Ready, right. So let me also arrange the start recording thing. Okay, perfect. Okay, it has already started. Do you agree with me that the recording has already started by someone else and not me?
Yes, I did start it.
Yes.
Yes. Okay, perfect. Thank you very much. So perfect. So it is the pleasure to have Pierre Pansu talking today. He comes from Université Paris-Saclay, and he will talk about the quasi-symmetric holder equivalence problem. So the stage is yours.
Thank you, Valentina. Well, thank you for offering me this opportunity to mention the different way, different door that opens to contact structures and sub-Riemannian geometry. The geometry of symmetric spaces, as alluded by Patrick Massot on Monday. So here is my way to get in. So let's start with the unit ball in a complex vector space C2. So at the same time, it's a symplectic manifold with convex boundary, and the complex manifold with strictly pseudo-convex boundary. I don't need to define these words anyway. It's an instance of non-compact symplectic manifold, let's say. So now the beautiful thing is that on the ball, first, there are plenty of holomorphic automorphisms, a huge group, which is transitive, but in fact much stronger than transitive. And simultaneously, there is a Riemannian metric, a complete Riemannian metric on the ball, which is invariant under all these holomorphic automorphisms. So it's a little bit difficult to draw pictures in 4 dimensions, but the picture you should have in mind is of the real hyperbolic plane. And what I'm speaking of is kind of complex version, but very many features are the same. So you have this complex hyperbolic metric that blows up near the boundary in order to be complete. So the boundary is at infinite distance from any point of the ball. And this is also negatively curved. And this is called the complex hyperbolic metric on the ball. So, and we call this space complex hyperbolic plane, and that's really suggestive and gives you the right intuition. It's like doing a hyperbolic plane geometry, but over complex numbers. So, but now there is an extra piece of data which is totally absent in plane real geometry. Well, not quite absent. Oh, wait. It's a family of sub-Riemannian metrics. So first, since we are dealing with a complex manifold and the boundary is a real hypersurface, this pseudo-convex guarantees that this the field of complex tangent is a contact structure. So one can speak of sub-Riemannian metrics adapted to this contact structure. And there is a particular family of sub-Riemannian metrics which are permuted by holomorphic automorphisms. In fact, there is one for each point in the ball. And now these metrics are conformal to one another in the sub-Riemannian sense, meaning that on the contact plane, they induce Riemannian metrics, which are all proportional at each point, but with different ratios of proportionality when you move from a boundary point to another boundary point. This is what I mean by conformal in sub-Riemannian geometry. Well, let's go a bit deeper in the geometry of that complex hyperbolic plane. So it contains plenty of remarkable surface, two-dimensional surfaces, which are totally geodesic. So totally geodesic means that the distance between points of the surface is either you take it as an intrinsic distance or as the restriction of the ambient distance, it's the same. So these remarkable surfaces are of two types. First, the complex lines. So each of them is a copy of a real hyperbolic plane of curvature -1. And you also have the family of Lagrangian planes. Each of them is perpendicular to a complex line, which is again a copy of hyperbolic plane, but with constant curvature, say -1/4. So as a Riemannian manifold, this four-dimensional space does not have constant curvature like a real hyperbolic plane, but the curvature varies between -1 and -1/4, and the extreme values correspond to these geometric elements, complex lines, and Lagrangian planes. So each Lagrangian plane intersects the boundary sphere along a curve which is Legendrian. And whereas the complex lines intersect the boundary sphere along curves which are transverse to the contact structure. They're called chains. So let me, I'm very unhappy not to be able to draw pictures in 4 dimensions, but let's try to draw one in 3 dimensions along the boundary. So imagine now I'm in the boundary. So here I draw a point. And this is a boundary point. And I imagine that's the end point of some geodesic that lives in the ball, in the 4-dimensional Riemannian manifold. So what do I, or is there a question?
I also heard something, but
No.
I could. No, maybe there's someone who left the microphone open.
Okay, no problem. So let me draw. So here is this point, which I think of the end point of the geodesic, and then through that point, there is a plane, the contact plane. And now let me draw the boundary of a Lagrangian plane. So this is a curve which is Legendrian. So it starts tangentially to that plane, and it does a rather complicated trip around the boundary, and then gets back like this. Whereas the boundaries of complex lines, every real geodesic, ordinary geodesic, is contained in a unique complex geodesic, a complex line. This forms a chain, a curve, which is transverse like this. Now there is more than one geodesic converging to that boundary point. And so more than one chain, a boundary of a complex line. And what do they look like? So they form a bunch of transverse curves, and their initial speed, their tangent at that point, in fact, they will fill in all transverse directions. They will, for each vectors, tangent vector, which is transverse to the contact plane, there is one chain that goes in this direction. And in fact, the same holds for Lagrangian planes and their boundaries called real circles. In each now horizontal direction, there is at least, oh, sorry, I didn't change the color. Then, oh, sorry, I made a mistake and I killed. Now, let's do all these real circles, boundary of Lagrangian planes. They will go in all directions in the contact plane, whereas the chains go in all possible directions transverse to the contact plane. So we see that the contact geometry on the boundary can be described in terms that depend on this Riemannian geometry inside the ball. So the geometry of complex hyperbolic plane determines this contact structure on the boundary. Let me. So the surface, the kind of rugby football that you see here, is simply what you obtain when you take one real circle, meaning boundary of a Lagrangian plane, and let it turn around one chain, the boundary of a complex line. So some kind of sphere foliated by these kind of helices, which are these complex, these real circles. So now let's wonder what happens when you perturb the metric, the Riemannian metric on the ball a little bit. So I will stay, let's say, among strictly negatively curved metrics. Can we still attach a boundary to this perturbed Riemannian manifold? Is this boundary smooth? And does the contact structure survive? So the answer is, well, some of it survives, but not all. So here are general facts about negatively curved Riemannian manifolds. So a negatively curved Riemannian manifold always have a visual sphere defined as equivalence classes of geodesics. And there are metrics, natural metrics, called visual metrics, defined on the boundary. In fact, you need to choose one point in the manifold M, and this determines a metric on the boundary. And the picture that you can see more or less explains how to define the distance between two boundary points AB viewed from the origin O, which is on the manifold M. You draw geodesics. By definitions, boundary points are equivalence classes of geodesics. So you draw these two geodesic rays from the origin to A and B, and they tend to diverge. So there is one distance, a capital R, from the origin O, where they sit at distance 1, let's say. And e to the minus r is what you take as a definition for the distance. And one shows that when we change origin O, you get a different metric, but which is conformally related to the previous one, and also by Lipschitz equivalent to the previous one. So this feature of complex hyperbolic geometry survives. There is a boundary. There is a family of metrics which are conformally related. Now, if the curvature is not perturbed too much, if it's still pinched, I did not write the definition of delta pinched here. Let me write it here on. So delta pinched means that the sectional curvature varies between -1 and delta, not minus delta, delta. So here delta is a negative number. So I claim that under this curvature assumption, delta pinching, then there is a canonical set of coordinates on M, which extends to the boundary. These are simply polar coordinates centered at any fixed point, fixed origin in M. And this goes to the boundary and allows to define a homeomorphism of the round sphere to this ideal boundary, this visual sphere of M. And now the fact the curvature is bigger than -1 says that the inverse of this map, the map from the visual boundary to the sphere, to the round sphere, is 1 Lipschitz, but in the reverse direction, it's merely Hölder continuous, C alpha, with alpha which is controlled by curvature pinching. Alpha equals square root of minus delta. And now imagine the space M is a perturbation of complex hyperbolic plane. What can I say can I compare their boundaries? I would love to be able to transport the contact structure to the boundary of this manifold M. And well, it does not quite work, but these two manifolds, complex hyperbolic plane, and if this other Riemannian manifold, which is by Lipschitz equivalent to it, are related, their boundaries are related by a homeomorphism, which is quasi-symmetric. So quasi-symmetric is a bit like by Lipschitz, but in conformal geometry, in a conformal sense. So it's a bit weaker. So let me show the definition. Maybe a larger picture will help. Oops, I did it wrong. No, okay. Here is the picture. So, sorry, no, I'm not in the right mode. I did it wrong. Here. So quasi-symmetric means that balls are mapped to quasi-balls. Well, you tell me, by Lipschitz maps behave in this manner. Yes, but what do I require? I merely require that the ratio of two radii is bounded. So which radii? The capital R here is the outer radius, so the radius of the largest ball that contains this quasi-ball, and small r is the inner radius, the radius of the largest ball, which is contained in the quasi-ball. So by Lipschitz would say that both capital R and small r are bounded. Quasi-symmetric merely requires that the ratio is bounded, which is kind of natural if you think in conformally invariant terms. And now these by Lipschitz maps and these quasi-conformal, quasi-symmetric maps are not quite smooth. And indeed, in general, one should not expect the visual sphere of a negatively curved manifold to be smooth. it has this quasi-symmetric structure, quasi-symmetric atlas. It also has an Hölder atlas, as I showed. And that's all we can tell. So that's not smooth enough to make sense of a contact structure. Right. So let's continue with this idea of deforming the Riemannian metric on this model, complex hyperbolic plane, while keeping curvature negative and bounded negative. And so again, I say a negatively curved manifold is delta pinched if the curvature varies between -1 and delta. Delta is negative. And I'm wondering whether it's possible by slightly deforming the metric to improve the pinching. And I defined the optimal pinching as the least delta, such that M is by Lipschitz equivalent to delta pinched, simply connected and complete Riemannian manifold. I tried to make the curvature as constant as possible, simply by changing the metric to an equivalent metric in the by Lipschitz sense. That's quite natural. And so by definition, the optimal pinching of real hyperbolic spaces, constant curvature spaces, is -1. For complex hyperbolic space, we know it's at most a -1/4 because the complex hyperbolic metric achieves -1/4. But can we do better? Is it true? Or rather, if not, this would mean that the optimal pinching would be equal to -1/4. And it's essentially an open problem. So I will propose an approach where sub-Riemannian geometry will play a role, that is relying on this boundary correspondence. So let me first introduce another definition, which is pretty much parallel to the previous one. We've seen previously that two by Lipschitz equivalent manifolds are related. Their boundaries are related by a quasi-symmetric homeomorphism, and that pinching of a negatively curved manifold translated into a control on the Hölder regularity of a homeomorphism with the standard ball. So now I take these two words, Hölder homeomorphisms and quasi-symmetric metric spaces. I put them together in the following notion. Given a metric space X, I consider all metric spaces which are quasi-symmetric to X. And for each of them, I'm wondering how I can map it, at least locally, to Euclidean space of the same dimension by a Hölder homeomorphism. And I can even assume that the inverse homeomorphism is Lipschitz. That's a little bit complicated definition, but we will practice it in a minute. So about our favorite example? So the boundary of the complex ball, of the complex hyperbolic plane. So this is a space which is locally quasi-symmetric to Heisenberg group, which I will denote by Heis. So we know that there is that the sub-Riemannian metric on Heisenberg group is Hölder related to the Euclidean or Riemannian metric. It's Hölder related with the exponent 1/2. And in fact, just the obvious coordinates on Heisenberg group achieve a homeomorphism which is one Lipschitz in one direction So the sub-Riemannian metric is larger than the left invariant Riemannian metric, for instance. And but the Hölder continuous with exponent 1/2 in the opposite direction. And this shows that this alpha exponent, this quasi-symmetric Hölder exponent for the Heisenberg group in its sub-Riemannian metric, is at least a half. Now I claimed a relation between these two numbers, the optimal pinching for a manifold M, and the alpha, the quasi-symmetric Hölder exponent of its boundary. And so I'll give a proof immediately now. So first, I repeat the two previous definitions on top of the slide. So you see on the left, in the Riemannian geometric manifold, you have these words pinching and by Lipschitz, whereas on the boundary, the keywords are Hölder homeomorphism, Lipschitz inverse, quasi-symmetric. And indeed, now imagine, oh, there is a typo. That M is a Riemannian manifold which is by Lipschitz to N, another Riemannian manifold, both of them negatively curved. Then this produces a quasi-symmetric homeomorphism between boundaries. Now, if I assume that N is delta pinched, then I get a Hölder homeomorphism with Lipschitz inverse from the round sphere to the boundary of N with a certain Hölder exponent alpha. And so the data of a pair of by Lipschitz negatively curved Riemannian manifolds give rise to the data of a pair of metric spaces. In fact, a triple, two metric spaces, the two boundaries plus the round sphere, a Hölder continuous homeomorphism of the round sphere to one of the spaces with a control on its Hölder exponent, and the quasi-symmetric map between the boundaries. So by definition, this gives a lower bound on this alpha QS, which is a supremum. And this lower bound is precisely square root of minus the pinching. So in this manner, we relate this pinching, optimal pinching invariant to an optimal Hölder exponent for its boundary, except that it's up to quasi-symmetric homeomorphism. And so this translates the search for the exact value, for instance, of the pinching exponent, the pinching number delta, into the search for an optimal Hölder exponent, maximal Hölder exponent alpha QS. Does it make the problem easier? Well, I'm not certain, but that's our strategy for a minute. So now, let me quote one result, which has to do with this optimal quasi-symmetric Hölder exponent, alpha QS. So it gives an upper bound. So it shows that you cannot approximate certain class of Riemannian metrics, all sub-Riemannian metrics by a Euclidean space of the same dimension. And the bound depends on the dimension, the usual dimension n, and the Hausdorff dimension. So I already explained to you that sub-Riemannian metrics have a Hausdorff dimension, which is an integer, which is strictly larger than the ordinary manifold dimension. And the upper bound, n-1 over q-1, is not very spectacular, especially when n is large, but at least for a Heisenberg group, which has a manifold dimension n equals 3 and Hausdorff dimension q equals 4, we get an upper bound of 2/3. So this implies a lower bound on the optimal pinching for a complex hyperbolic plane, since its boundary is quasi-symmetric to Heisenberg group. And the lower bound we get is not -1/4, it's -4 nth, minus the square of 2/3. So it's not a scoop. These had been previously obtained by different methods. So in fact, I don't care that much about that pinching problem. It was more like a motivation to study Hölder homeomorphisms between Riemannian and sub-Riemannian metrics, and with this quasi-symmetric bias. And right. So now, I'd like to get back in the history. So this is a rather recent result, whereas the story starts much earlier. This starts with Gromos' book on Carnot-Theodori metrics seen from within, some nearly 30 years ago, and where he sets the following problem, the Hölder equivalence problem. So there, he wonders, yes?
I see there's a question,
Yes.
maybe.
Yeah, I mean, I think maybe it's a stupid question, but just to make sure. So you said that sometimes the visual boundary, the metric structure you get there need not be sub-Riemannian, right? Is that correct?
That's right. Yeah.
And but could it happen that instead of like a contact thing, you get a sub-Riemannian thing that is not contact?
That's true. In fact, here are a family of examples. Start with a Carnot group. Are you familiar with a Carnot group?
Yes.
That's a Lie group equipped with a left invariant sub-Riemannian metric, which admits a group of dilations, of homostheties. So these are the local models for sub-Riemannian metrics. So start with the Carnot group. Then you can form a semi-direct product, which will become a Lie group of one more dimension, a solvable Lie group. And this admits a Riemannian metric of negative curvature, whose boundary is the Carnot group you started with. So you may dislike, because these visual boundaries are topological spheres, whereas the Carnot group is a topological Euclidean space, but this means you need to add a point at infinity. So that's an interesting family of examples of invariant metrics, Riemannian metrics on Lie groups, which have negative curvature. And we can achieve in this way all, as boundaries, all Carnot groups.
Thanks a lot. Then maybe, so then at the infinity point, the structure presumably is quite bad, I would imagine. Or?
Yeah, that's right. It's substantially different.
Yeah. Thanks a lot.
So, but this is again a very regular, very smooth example. You see there are Lie groups in the picture, but one can describe other examples of negatively curved manifolds whose boundary is kind of it's like Riemannian or sub-Riemannian, but broken along a dense set of codimension 2 submanifolds, countable dense. So it's kind of broken Riemannian geometry. There is a nice family of examples like this. And the general case is, you know, it's a negatively curved metric is not a rigid space. You can, it's a negative curvature. This is an open condition. You can deform the metric a bit as you like, and you expect the geometry at infinity to be affected in a rather bizarre manner. It's very flexible. So this construction produces a class of metric spaces which is maybe which is rather large, let's say.
Well, thank you.
So now let's get back to sub-Riemannian geometry and this question by Chromos. So okay, we know that there is a sub-Riemannian manifold can be compared with a Riemannian metric on the same manifold. So this gives a homeomorphism, which is Lipschitz in one direction, Hölder in the other, where the Hölder exponent is 1/2 for two-step sub-Riemannian metrics, like contact structures, but it's 1/3 for 3 steps, and so on. It gets a little bit worse. It's not very good. So, and the question by Gromov is, can one do better? Can one find a better set of coordinates where the sub-Riemannian metric looks more regular than in the obvious coordinates? And that's a difficult problem. So in order to formulate Gromov's results, I'll use some notation, again, introduce some kind of optimal Hölder exponent, the best, so the largest exponent, Hölder exponent alpha that you can achieve for a set of coordinates on your manifold. And here are Gromov's results. So first, for every metric space, if the topological dimension and the Hausdorff dimensions are different, then you get a bound, n over q. In the sub-Riemannian case, you can get n-1 over q-1, which is a number we've seen previously. It's the same I get for the quasi-symmetric version of alpha. So which is a little bit better. That's an improvement on the previous one. And in the special case of contact manifolds, then Gromov can even improve again upon the two previous bounds. A bit later, I will explain how it proceeds. But now, this suggests a whole set of questions, and it would be convenient to first set the questions and see how these results answer these questions. So in the by Lipschitz working group, you've already discussed many of these questions, I suspect. So again, if you start with the contact structure or more general distribution, I pick an adapted sub-Riemannian metric, and I observe that locally any two choices will be by Lipschitz equivalent. And so if I'm on a compact manifold, this local by Lipschitz equivalence will be even global. And now any value by Lipschitz invariant notion will give rise to an invariant, a corresponding notion in contact topology. And so now we can introduce by Lipschitz maps, or more generally these quasi-symmetric maps I defined a few minutes ago. But also these more analytic classes of maps like Sobolev maps, L1P maps which have derivatives, first derivatives in LP, or merely horizontal derivatives in LP, or Hölder continuous maps. And all these classes may make sense now in contact topology, and we are wondering whether these larger classes have the same effect on contact structures, let's say, as diffeomorphisms. So we are wondering what is the classification of contact structures in each of these categories. So I've seen that you've discussed the case of the bi-Lipschitz category already at length. Well, I like the quasi-symmetric category, as you have guessed, and also the Hölder, and this is the only result I can state and prove for you today deals with the Hölder case. And so what does Chromos say about the Hölder case? So when he states that the Hölder exponent of let's say the Heisenberg group of a contact 3 manifold is at least a half. And what this means is that Hölder maps with exponent less than a half, they simply have nothing to do with contact geometry. They make no difference, or they make little difference between contact sub-Riemannian and Riemannian. So they're just useless. But now, and Gromov's question, what is the optimal value, the optimal Hölder exponent between Euclidean 3 space and Heisenberg group? Then this can be reformulated as what is the bound, the threshold below which Hölder maps have very little to say about contact geometry. So apparently 2/3 could be such a threshold. Well, 2/3 or a half. So there is some evidence in favor of 2/3, and this is a recent result by Wenger and Young. Well, they are not able to produce homeomorphisms from R3 to Heisenberg group, which are C alpha with alpha up to 2/3, but merely a proper degree 1 maps. So maps which are not bijections, but at least homotopically speaking are bijections. So that's technically an important input, because it indicates that arguments that would rely only on homology or homotopy of Hölder maps will not succeed in improving upon Gromov's bound of 2/3. Right. So this threshold where Hölder maps really interplay interestingly with contact structures in dimension 3 is unknown. Something between 1/2 and 2/3, maybe one half, maybe 2/3. So the question becomes, imagine you have two contact manifolds in dimension 3, let's say compact, and assume that they are Bi-Hölder equivalent with exponent now bigger than a half, excuse me, bigger than 2/3, must they be contactomorphic or not? And this is a really open question. And it's irritating because I'm unable to say anything about it. But to some extent, maybe we understand better higher dimensional and higher step sub-Riemannian metrics. And I will simply say a few words on this. Here is an invariant that one can attach to a manifold, a filtered manifold, a manifold with a distribution. It's a filtration of differential forms by weights. I don't want to go through a complete definition, but it's kind of intuitive. In 3 dimensions, one forms on a contact manifold come into 2 qualities. You have the one forms which vanish on the contact plane, which are proportional to the contact form, and which have weight 2, and the others which have weight 1. And this filtration by differential forms induces a filtration of cohomology. And now this can be shown to be by Lipschitz invariant. There is an analogous filtration by weights of cohomology, which is defined by using, instead of differential forms, cochains. One can use, well, let's say Alexander-Spanier cochains. That's a bit technical. Let's say cochains which are more naturally transported by homeomorphisms. And then this version, which can be compared with the filtration with differential forms, is by Lipschitz invariant, obviously, by construction, and even covariant under Hölder homeomorphisms. And so, and in particular, invariant for Hölder exponents with Hölder maps with exponents close enough to 1. So this seems promising. And but unfortunately, this filtration of cohomology is always trivial for contact manifolds. And in fact, this is the first consequence of Riemann's theory of differential forms adapted to contact structures and higher dimensional sub-Riemannian structures. So here is an example of a tool which would be available for sub-Riemannian manifolds, but not for contact. It's a pity. So I'm wondering whether this kind of questions about by Lipschitz or Hölder quasi-symmetric equivalence of sub-Riemannian manifolds, whether the contact case possibly would be the hardest case. What time is it? Do you?
It's 4:05.
Yes.
So you like 15 more minutes?
Yes. So maybe what I'll do next is maybe mention another set of questions. And if there remains some time, I can give you some hint on the proof of these upper bounds on Hölder exponents by Gromov and my argument, which is inspired by Gromov anyway. So let me mention a different kind of problems dealing with non-compact contact manifolds. You've seen the route I followed to reach compact contact manifolds was starting from a non-compact Riemannian manifold and its large-scale geometry. And now, why not study the large-scale geometry of sub-Riemannian manifolds, including contact manifolds? So here, it's convenient. I really need to compare Riemannian and sub-Riemannian manifolds. And they will never be by Lipschitz because even locally, this is not true. They don't have the same Hausdorff dimension. So let's introduce a weakening of the notion of by Lipschitz, which ignores what happens at small scales. This is called quasi isometry. So a quasi isometry is a map between metric spaces, which is essentially onto, let's say, up to bounded distance, meaning that the image, every point in the range Y sits at distance from the image of the domain less than some constant. This is what I mean by onto up to bounded distance. And otherwise, I want the by Lipschitz inequality. Why did I write only one of them? I really mean both in both directions. Let me apologize for that. That's a typo. Except that I want it only for large distances. Distances larger than some constant. I just put one to designate a constant. Right? So, example. If you start with Heisenberg group and compare a left invariant Riemannian and sub-Riemannian metric, of course, they are not by Lipschitz equivalent. They are not even locally by Lipschitz equivalent, but they are indeed quasi-isometric. Because if you discard the short distances, there's no problem in comparing those distances. In fact, the Hölder comparison at small scales suffices to imply the by Lipschitz inequality at large scales. That's a general principle. So now the next thing you want to do when you speak of geometry on non-compact manifold is put a constraint on the local geometry called bounded geometry. So I say a Riemannian manifold has bounded geometry if all balls of radius 1, let's say, are by Lipschitz equivalent to the unit Euclidean ball with a uniform constant. So in each ball looks more or less the same. Each ball of a fixed radius. This is the notion of bounded geometry in the Riemannian case. What do I call a sub-Riemannian manifold of bounded geometry? Well, I will be a bit lazy and follow an indication given by Patrick Massot. He explained to us that given a contact manifold and a sub-Riemannian metric, it can be extended into a Riemannian metric in a canonical manner. Patrick also added an extra parameter, which was a speed of rotation. But let's say that this speed is equal to 1. And so the sub-Riemannian metric extends canonically to a Riemannian metric. And I'll say that a sub-Riemannian manifold has bounded geometry if the corresponding Riemannian manifold has bounded geometry. Now, so when this happens, it seems to me that both metrics are automatically quasi-isometric. And now I'm interested in the converse question. Oops, sorry. Sorry. Now I start with a bounded geometry Riemannian manifold in dimension 3 with a contact structure. And I'm wondering whether I can choose an adapted sub-Riemannian metric, again of bounded geometry, which is quasi-isometric to the initial Riemannian metric. So what I have in mind is the following. So imagine the contact structure rotates little, has a bounded rotation speed, as Patrick mentioned. Then the sub-Riemannian metric, which is simply the restriction of the Riemannian metric to the contact plane field, will be of bounded geometry, and the corresponding canonical Riemannian metric will be quasi-isometric to the original one. So what I'm imagining now is that you have that the contact structure rotates a lot and faster, kind of crazy, like crazy. And so we're really getting potentially a different quasi-isometry type. So maybe you need to reparameterize, to transport the contact structure by a diffeomorphism in order to reduce its rotation speed. So that's a hard question. So again, how would I approach the problem? Let's say on the manifold R3. So I'm on R3, I'm given a bounded geometry Riemannian metric, but I suppose that no contact structure is given at first. And now let me construct a contact structure with bounded covariant derivatives. In other words, I'm trying to do the Lutz theorem, who states that every 3-manifold admits a contact structure, except I take into account the given Riemannian metric, and I do this construction with controls on the rotation speed, on the covariant derivatives of the contact structure. So that's it seems to me rather likely that this is possible. And so I obtain a contact structure and a sub-Riemannian metric simply by the metric is by restriction of the given Riemannian metric, and I expect it to be quasi-isometric to the given Riemannian metric. So in this way, I obtain an over-twisted contact structure with a controlled, which achieves the quasi-isometry type which was prescribed. And now I use Eliashberg's theorem that states that on R3 there is only one over-twisted contact structure. And so I'm done, except to have shown that sub-Riemannian metrics adapted to the over-twisted contact structure on R3, they achieve all possible quasi-isometry types. But what about the tight contact structure? I have no idea how to handle it. So does this question make sense to you?
Please.
Yeah, so I want to say you mean the unique contact structure which is over-twisted at infinity, because if you look at contact structures that are tight in the complement of a compact subset, then there are more of them.
Ah, yeah.
But I mean, the construction you have in mind will indeed produce over-twisted disk as far away from
As
the
far
origin.
infinitely far, yeah. Mm-hmm. Ah, you're right. So when I said the over-twisted, you mean I should write the contact structure which is over-twisted up to infinity, right?
Yes. Yes, otherwise because you can take another twisted contact structure on S3 and remove a point, and you get a contact structure on R3 which is tight in the neighborhood of infinity, because in S3 when you near each point you've got a tight ball by Benkin, and so so they are contact structure.
Right. So.
But I mean, that's
the statement I wrote is misleading. It applies only to the crazy over-twisted, the one which is infinitely many times over-twisted.
Yeah, but I mean, the picture that people always draw of an over-twisted contact structure is invariant under translation in one direction. So that one is over-twisted at infinity. I mean, it's not crazy. It's, the usual one is over-twisted at infinity.
Mm-hmm. Okay, thank you. Thank you for this correction. Well, I could stop there. Yeah, I think it's due time to stop there. Thank you very much for your attention.
Thank you very much for the beautiful talk.